Hey everybody, I'm hungry and I'm going to make a sandwich that is my favorite. I like to make a barbecued cow, and I like this exothermic reaction that is the combustion of propane. Now my grill's super old, so the way I light it is I just sort of use another exothermic reaction where I just fling matches at it because my igniter switch is broke from a great distance, and it's really scary because propane's heavier than air. Ah! Okay, let's go talk about the exothermic reaction that is the combustion of propane next.
Well, howdy everybody, howdy. I'm here, I'm in one piece. Got a nice barbecued cow sandwich in my tummy. Okay, here we go. We're going to calculate the delta H, standard delta H, for the combustion of propane. Now, anything that is combustion, as you probably know, that is the reaction with oxygen. So C3H8 plus O2 goes to make, and the products of combustion are CO2 and water. Oh boy, quick balancing trick, right? 3 there to balance the carbons, and then a 4 there to balance the hydrogens, and it's a 6 and a 4 is a 5 O2s, right? Even though it don't matter, because when we go and plug this through the table, we have an element in there, and so the way we set it up, it's the sum of the delta HFs of products, stuff on the right, minus sum of the delta HF of all the reactants, stuff on the left. Watch out, don't get it backwards. You'll be able to tell if you get it backwards, and I'll show you about that later. And so what that's going to mean is I'm going to look up, this would be the delta HF, 3 times the delta HF of CO2, put a little parentheses around that, plus 4 times the delta HF of water. We'll call that water gas, minus the delta HF of C3H8 plus the delta HF of 5 halves. Delta HF, running out of room, O2. And it's okay that I ran out of room. You know why? Because this bad boy is going to be 0. We got an element in there. 0. 5 halves times 0 is still 0. Now we're going to go and take our table out and do what we call in science some looking at it. And so we're looking over by where we got all this carbon stuff. There's propane. That'll come in later. Sorry, I was just going in order of the way I see them. There's CO2, and we'll have to look up that number. Here's water vapor. And oxygen, of course. You'll notice these are not the elemental forms of oxygen there. Those are something weird. And so what we're going to do is take them right, and you do the same with me, please. Go and take them right out of your table there. And make sure you don't look at the wrong thing. Make sure you don't, do that goof, which I've done several times. So this would be 3 times minus 393.509. We'll leave the units off. It's kilojoules per mole, but just to not clutter things, we'll leave them off for now. Plus 4 times H2O vapor is minus 241.83, minus the delta HF of 1 mole of C3H8 is minus 104.7. Cool. Order of operations. Let's do those multiplications on the left first. 393.509 times 3 equals minus 1,180.527. That's going to get added to, to 4 times 241.83 times 4, negative 967.32. Hey, look at minus, negatives, plus a positive, plus 104.7. So let's crank out those three things. 1180.527 negative plus 967.32 negative plus 104.7 is a whole bunch of energy. Delta H F, no, a delta H, a reaction, minus 2,043.147 kilojoules per mole. There is our answer, my friends. And so what we can do in the future is we can, use that like a little thing I've dreamt up for you. Kind of trivial, but if you got a gas grill, it's not trivial. A typical cooking gas cylinder contains 14.2 grams of propane. Thanks to Google. I Googled it, so it must be correct. So that's kind of a joke, but Google's okay. If it makes sense. It feels like about 30 and a little bit pounds when I go and get it filled up and I exchange one for another. It feels like it's good and heavy. And by the way, it's a liquid in there. It's sloshing around. So how many kilocalories, because that's food calories, I thought that would be cute to do, would this provide? So we're going to use our answer. Now here, we don't need to know about sign. It's more of a magnitude, but I'm going to start with that number, and then we're going to convert kilojoules per mole to how many moles. So I need to know how many moles 14.2 kilograms is. That's, of course, it's 14.2 kilograms of C3H8. 1 kilogram is 1,000 grams of C3H8. And then, oh boy, 3 times 12.01 is, 36.03 for the carbons. Hydrogens are $1.01 a piece, so that would be plus 8.08. This is 44.11 grams per mole. So now all we've done is find out how many moles we've got so far. So 14,200, I'll just do the first step, divided by 44.11 grams per mole. This is 300 and, let's just call it 322 moles. I rounded to 3 digits. From our previously completed calculation, 2,043 kilojoules. We want food calories, 4.184 kilojoules, 1 kilocalorie. Hey, let's even go further. 370 kilocalories. 1 package of ramen noodles. How many ramen noodle packages would that be like burning? 322 times 2,043 divided by 4.184 divided by 370. That would be 425 packages. of ramen noodles. And I'm sure propane burns cleaner than that, but if you could provide enough oxygen to make that happen, that would be over 400 packages of ramen noodles. And so in your mind, put those all into a big old barrel and then combust them. And the flames would probably be glorious and reach into the sky and be seen from an airplane or something. Okay, don't do that at home. Well, you know, hey, I'm just, if you can do it safely. I'd rather burn a ping pong ball, if you would. Old ping pong balls are made of nitrocellulose. It's glorious. So anyhow, I digress. Let's do another problem. That took 10 minutes. Let's do another one that's even harder. And then I think I'll have used you up for a day. I'll have burned you out. Oh, jeez. All right, now, interestingly enough, you're probably wondering, like, hey, where did all these numbers come from? Especially the carbon-hydrogen compounds. And I'll tell you right now, folks, a lot of these were arrived at very similar to the way we're doing this. So you would put this substance, we're going to make it exciting, we're going to make it TNT, the explosive, which, by the way, was discovered by Alfred B. Nobel. And when Alfred B. Nobel found out that his discovery, his discovery of trinitrotoluene, there's the three nitros, they put oxygens on things for them and do combustion, then I guess that he wanted to compensate for the fact that his invention was used so much in warfare that he invented the Nobel Peace Prize and, of course, the Nobel Science Prize. But anyhow, the way you would find out the delta H of something is you would put it in something called a calorimeter, a bomb calorimeter, nothing to do with the fact that this is an explosion, just a compartment, and you would carry out combustion. You would find the enthalpy that was passed on to something like water, and while I'm at it, here's a diagram of a bomb calorimeter where this particular type of thing could be carried out. So you kind of see it's nothing really more than just a bucket of water with a very sturdy canister that can be pumped full of oxygen, so the pressure don't change because it's got to be enthalpy, it's got to be heat at constant pressure. And then you measure that amount of heat passed to the water. You do something like this. Here we're being told that it's 10,153 kilojoules for this reaction, which, by the way, has 2 moles. And so let's go ahead and set it up as products minus reactants, except this time we don't know the answer. So I'll go ahead and write it out. Would be sum, and this would be, I'll just do it, sum of the products. So this would be delta HF 12 times the delta HF of CO gas plus 5 times the delta HF of H2 gas plus 3 times the delta HF of N2 gas. This is a big long reaction. Plus 2 times the delta HF of carbon solid, big old parentheses, minus 2 times the delta HF, I'm just going to call it TNT. As a matter of fact, you know what I'm going to do? I'm going to call it X. And you know what's kind of nice here is equals minus 10,153. Ooh, you know what? I'm not going to call it X. Well, I'm going to call it X. 2X. We got 2 moles. Watch out for that. All right, that's kilojoules, but there's 2 moles in there. We're going to have to find X, and either you can find this value here, but you better divide it by 2 because there's 2 moles, and we want to find its delta HF in moles. But you know what? We get cut a huge bunch of breaks here. Because as this decomposes into 1,000,000 different molecules, which is, by the way, what explosion reactions usually do, that's called decomposition. 0, 5 times 0, 3 times 0, 2 times 0, those are all the elemental forms. And so this is all going to boil down to 12 times the delta HF of carbon monoxide minus 2x equals 10,153. By the way, I'm kind of wondering if this is wildly positive or not very negative, because TNT doesn't sound like a very stable molecule to me at all. That's the whole point of it. So now we're going to go to the table. So let's just go ahead, and now we're using numbers. 12 times the enthalpy of formation of carbon monoxide minus 110 point, making sure I didn't look it up wrong, 525 minus 2 times the delta HF of TNT, I'm just going to call that X, equals minus 10,153. Cool. Let's go ahead and crank out that, distribute that 12 through. So 12 times 110.525 is minus 1,326.3 minus 2x equals minus 10,153. I'll leave the units off for now. We know it's going to be in kilojoules per mole when we get done with this. I'm running out of paper maybe. Okay, so what I'm going to do next is I'm going to get my x's all isolated to one side by adding to both sides the positive 1,000, or adding 1,136.3. That would, of course, get rid of it on the left. And on the right, we would then have whatever, 10,153 negative plus 1,136.3. That would be minus 9,016.4. I need more paper. Cool. I got a little bit of paper. Okay. How about this? Double negative. X, I just multiplied both sides by -1 because I could. 9,016.4 divided by 2. Holy cannoli. Delta H, or X, is 4,508.2 kilojoules per mole. We always got to remember what X is, right? This is not math class. This is where X represented something. The delta HF of TNT is positive 4,508.9 kilojoules per mole. That to me is extremely surprising. Now, but here's the thing: a mole weighs a lot. That's a big old molecule if you add up its molar mass. So that would be more mass than a mole of a lot of things. But there ain't nothing on this table that's that positive. Even last time we were talking about acetylene being 226 to the positive. And there's some weird things on here that are very positive because they're not very thermodynamically stable. How about ozone? That gets created in the atmosphere from lightning. That's how positive that is. So this molecule of TNT does not want to stick around. It wants to become its elements. And so that's a good example of when a delta HF being very positive tells the reader of it, that number, hey, this is an unstable molecule. And of course, you know, this is what you would use to blow holes in mountains to make tunnels, and I'll use peaceful examples. And it's very unstable because it's dynamite. So, I don't know. Thanks for watching. Next time we'll talk about manipulating delta HF reactions using something called Hess's Law. Until then, stay cool, everybody. Bye.